Today we're looking at 7 geometric sequences. So if you recall, we did arithmetic sequences, which we're looking for a common difference. Like say I had 2, and then 5, and then 8. I would be adding 3, My common difference would be 3. And that would be like an arithmetic sequence. What we're going to be doing today is a little bit different, but very much the same as well, in looking at a geometric sequence. And in a geometric sequence, there's not a common difference, but instead a common ratio between consecutive terms. So each term is going to be found by multiplying the common ratio to the previous terms. So for example, if I have a sequence that goes 1 to 5, 5 to 25, 25 to 125, I'm multiplying every time by a common ratio of 5. So 1 times 5 is 5, 5 times 5 is 25, 25 times 5 is 125. So this right here is a geometric sequence with a common ratio of 5. Right? So let's try and take that little bit of information and extend some geometric sequences. If I look at example 1, part A, I have a sequence that looks like it goes from 1 to 3, 3 to 9, 9 to 27. So the first thing I should think is, what is my common ratio? Okay, I have 1 to 3, and then 3 to 9. This looks like I could either be adding 2 or multiplying by 3 to get from 1 to 3. To get from 3 to 9, I could be adding 6, or I could be multiplying by 3. So it looks like in order for these things to be common between all the terms, I'm going to be multiplying by 3. 9 to 27, again, multiplying by 3. So, if I want to continue the sequence, what are my next 3 terms going to be? Well, if I look at my sequence, I'm multiplying by 3 every time. So that means that I have to multiply 27 by 3 as well. So what do I get when I multiply 27 by 3? $81. And then I'm going to have to multiply that by 3 again. What do I get? 243. Multiply that by 3 again. What do I get? 729. Hopefully you're doing that along with me. So that when we go over to B now, we can move a little bit quicker. I'm looking at B and I'm seeing 80 to negative 40. Okay, that's a huge jump. And then from 40 to 20. Okay, that's interesting. I went from a positive number to a negative number, from a negative back to a positive, and then a positive, I'm going to go back to a negative. So if I'm thinking about a common factor here, it looks like I'm going to be multiplying by some sort of negative number. So from 80 to 40, what number would I have to be multiplying by to get there? Well, 40 is half of 80, so I'd have to be multiplying by negative 1/2. From 40 to 20, does the same thing work? Negative 1/2 will get me to 20. Negative 1/2, again, will bring me back to negative 10. So now if I want to continue, I'm going to have to do negative 1/2 of negative 10, which brings me to a positive 5. I'm going to have to do negative 1/2 of 5, which will bring me to a negative 5 over 2. And then lastly, a negative 1/2 of 5 over 2, which will bring me back to a positive 5 over 4. Once you feel comfortable with that, let's move on to example 2. In example 2, what I want to do is graph the geometric sequence and then see what it looks like. So I'm going to switch over to a different color here. And what I'm going to do is plot the position. So basically this sequence would look like this. 32, 16, 8, 4, 2, dot, 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 dot. So this is the first position, this is the second position, third, fourth, fifth. That's what these numbers mean. 1, 2, 3, 4, 5. That's the position in the sequence. So 32 is in the first position, 16 is in the second position, and so on. So what I want to do when I graph this is graph position versus term. So on the x, I'm going to have my positions. On the y, I'm going to have the term. And that's what I'm going to be graphing between. So 1 is going to bring me to 32. Now obviously I don't have 32 blocks here, so why don't I 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Don't even have enough for that. So maybe I do 4, 8, 16, 20, 24, 28, 32. Why don't I go there? Okay, so each of these is going to be worth 4. 4, 8, 16. Alright, and second term is going to go to 16. Third term is going to bring me to 8. Fourth term is going to bring me to 4. Fifth term brings me to 2. So what does it look like is happening here? This should look familiar, this type of curve. So what do you notice about the points? It looks like a geometric sequence, when graphed, looks a lot like an exponential curve. Right? And that's exactly what we should find out. Just like when we graphed an arithmetic sequence, it looked like a linear curve. When I graph a geometric sequence, it looks like an exponential curve. When you feel confident with graphing, we can move on to the next page. Now here on the next page, I want to talk just a little bit about building the formula for a geometric sequence. Alright, so we talked about the position. The position is basically saying, what term are we talking about? We're talking about the first term, the second term, the third term. Okay, so when I have position 1, 2, 3, 4, all the way up to the nth position, that's just any number I could possibly think of. It could be the 1001st term. Now, the next column, we're talking about the a sub n. And that's going to say to us, I want that actual term. So I want the first term. I want the term that's in the first position. I want the term that's in the second position. I want the term that's in the third position. The term that's in the fourth position. Or the term that's in the nth position. First term, second term, third, and so on. Nth. Now I want to write them using a sub 1 and whatever common ratio I have. So I can express the first term, the a sub first term, as a sub 1, obviously, plus nothing else. It's literally just a sub 1. If I want to express the second term in terms of the first term, it would be a sub 1, and then what? If I wanted to get from the first term to the second term, all I had to do was multiply by the ratio. So this is going to be a sub 1 times whatever the ratio is. Okay, easy enough. Now, what about if I wanted to write the third term in this same way? Well, it would be a sub 1, and to get to the second, I have to multiply by the ratio. So now it shows me the second term. And if I want to get from the second to the third, I have to multiply again by the ratio. So times r again. So what's that equal to? A sub 1 times r squared. Okay, alright, this is starting to form a little bit of a pattern. Let's see if I can make it work for the fourth term. It's going to be a sub 1 times the ratio gets me to the second term, times the ratio gets me to the third term, times the ratio gets me to the fourth term. So what's this simplified? A sub 1 times r to the 1, 2, 3, third. So what it looks like is there's some sort of relationship here. To get the second term, I had to multiply by r to the first. To get the third term, I had to multiply by r squared. To get to the fourth term, I had to multiply by r to the third. So if I want to write to the nth term, it's going to be the first times r to the n minus 1. See, n was 4 here, so I raised it to the n minus 1. 4 minus 1 is 3. N was 3 here, so I wanted to raise it to the n minus 1. 3 minus 1 is 2. So any time that I want to get any term, I can multiply by r raised to the n minus 1. And let's see how that works in numbers. Let's say my first term is a 1. Alright? Easy enough, a sub 1 is a 1. Now if I want to get the second term, let's say I have, I don't know, a ratio of 5. Alright, so my ratio, I'm going to multiply by 5, and I get 5. That's my second term. Now if I want the third term, I'm going to again take the initial 1, but this time I'm going to multiply by r squared, the ratio squared. So that's going to be times 25 equals 25. The next one is going to be 1 times r cubed, 125. And lastly, if I wanted any term, I would multiply by 5 raised to the n minus 1. Alright, now let's take a look at a formula. We kind of just made it right up here, but let's write it out and explain exactly what everything means again. The equation for a geometric series, sequence, is going to be whatever term you're looking for, a sub n, is going to be the first term, a sub 1, times the ratio to the n minus 1. Now what do all these things stand for? A sub n is the nth term, whatever term you happen to be looking for. R is the ratio. A sub 1 is the first term. And n is the position. The position you're looking at. So a sub n implies the nth position, and what you're looking at is the nth term of the series. The last thing I want to look at, again, is a real-life application of something like this. And what it is clicking the zoom out button on a mapping website, and how it affects the map's vision and what you can see, the distance that you can see on that map. So what this is saying is that when you click that zoom out button, the website doubles the side length of a square map. Alright, so if I click out once, my side length is 5. If I click zoom out twice, now the side length is 10. If I click out 3 times, the side length is 20. Alright, so basically what I have here are terms of a sequence. First term, second term, third term. And what does it look like my common factor is? I go from 5 to 10, 10 to 20. I'm pretty much multiplying by 2. So that's what it looks like my factor is. So write an equation for the nth term of the geometric sequence. Well, a sub n should equal the first term. What's the first term here? It's 5 times that ratio, that common ratio, which we just said was a 2, raised to the n minus 1. Done and done. Find and interpret a sub 8. So a sub 8. I replace n with an 8. So I also have to replace n with an 8 everywhere else in the equation. 5 times 2 raised to the 8 minus 1. So 5 times 2 raised to the 7th. All right, what is 2 raised to the 7th times 5? Well, what that comes out to is 640. So what does that mean? What is that? How is this important? What is this even telling me? I know that I got 640. Yay, I got the right answer. Who cares? Well, this tells me that the 8th term in the sequence is 640. So let's say I plop it into this whole table over here. Got dot, 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 dot. 8th term, 640. That means that I've clicked zoom out 8 times, and now the side length in miles of my map is 640 miles. That's what that means. After how many clicks on the zoom out button is the side length of the map 2,560 miles? How am I supposed to figure that out? How about you try that one at home, and I will check, see what you guys get in class. So what I'm looking for, if I add back into this table, is I'm looking for what term will fill in a 2, 5, 6, 0 here. What is that term which makes 2560 over there? Good luck!